Hi there. So we will cover the rest of lab 11 in this video. This will be our class for Friday. And so I want to show you, this is listed as due Saturday. You should do it for Saturday. I have it available until Monday, that's the 15th, in case you have any questions. So if you have any questions on the lab, bring them in on Monday and I will answer them and accept your lab until Monday night. Similarly, I made homework 7 due Monday night in case you have any questions, but you should work on it this weekend still. It's going to be a lot to finish if you leave it all till Monday. So, and if you get stuck, that's when I want you to bring questions. That's when I'm here to help you. All right, so we are going to cover the t-test. This is the hypothesis test for a mean. And we'll start with using the dolphin example. We found a confidence interval for that mercury concentration of dolphins. Now we're going to do the same test to determine, is it safe to eat the dolphins using a p-value. Okay, so this involves using a t-distribution, which I described as being similar to the z-distribution, the normal with 0 mean, standard deviation 1, when the sample size is big. And so we are using a standardized statistic, which we get from the mean minus the expected mean divided by standard error. So I'll show you how we get this using this formula. So first we need to revisit our data. If you go to the dolphins example, here was our data. Let's copy that. Here's how we're going to find the t-score. T-score is going to be the mean, the observed mean, which was 4.4 x bar, minus the null mean divided by standard error. So two things we haven't specified what they are, the null and the standard error. We have calculated the standard error. That doesn't change. So let's go to where we found the standard error in this one. You can copy that, paste that code. And the null mean is what you expect or what you want to compare against. So remember how in this example, the end of the dolphins example, we said, is it safe to eat? Does it satisfy being less than 0.46? We're going to use that as our null value. Anything we're comparing against, that's the null. Okay, so that's how we get the t-score. You can check that. Okay. And so I've put in the hypothesis. The hypothesis for the t-test is always, is your observed concentration or your observed mean, I should say mean concentration here, is it the same as some expected value or some baseline measurement? And the alternate could be either, do I want it to be less than, greater, or just not equal, less than or greater than. In this case, we're really concerned if the dolphin mercury concentration is above our limit. So that's going to be the alternate hypothesis. Okay, so now let's find the p-value and the t-score. We already found the t-score. So let's put that actually down here. There's the t-score. So the p-value is going to be, let me see if I can draw on here, annotate, if it lets me. The p-value is going to be the probability of observing something greater than what we found. So we found our t-score to be, what was it, 7.46? 7.46. And 0 is always the center of the t-distribution. We have degrees of freedom n minus 1. So we're finding the probability of observing something greater than what we did. So it's that. Okay, so that's something y'all can do now. And then check it with what I'm getting here. All right. So that's my p-value for the situation. And here's an interpretation. This value, 3.22 e to the -7 means I have 6 zeros. And then the 7th decimal place is after the 2. Oh, it should be 322. That's a small value, very low p-value. So we reject the null hypothesis that mercury content is the acceptable allowable amount, 0.46. Is that what it was? Yeah, 46. It's not the null value. It's most likely something greater. And so, no, it's not safe to eat. And it confirms what we did in the confidence interval in the previous section. All right, so you will have to then do this exact same process. See if I can clear my annotations. Clearer. For the whitefish. So to now determine if the whitefish are safe to eat, you can use the exact same process, okay? So I have two more examples I want to cover. Are runners getting faster or slower? This is a case where we have two different situations. Like there was a race, I think it's a marathon race, cherry blossom race in 2006. There was a mean time of 93.27 minutes. Now that doesn't seem, that's too long for a marathon. Anyhow, if you're a runner, whatever that means, we're curious, is this time getting faster or slower from the previous race? Or sorry, is the next race, 2017, faster or slower? Okay, so it looks like people are getting slower, right? In 2017, the mean time is slower. But is that based off the sample size? Is that due to chance, or is there maybe indication that there's something else happening? So how do we test this in this case? The null hypothesis, if we're looking at 2017 being our data, the null hypothesis is that the mean, that's the data that we collect. So the mean 2017 race time is the same as 2006. It's not changing, which is 93.29 minutes. That's our null value. And so the null hypothesis, the alternate is the mean race time is not the same. So I could say mu is not equal to. Mu is the population mean. Okay, so think about these carefully. These null hypotheses are what everything, these hypotheses are what everything hinge on. That should be plural. Okay. Oh, we should check. Did these conditions describe, satisfy our conditions for being nearly normal? And so we can go review up here. I think it was, where was our conditions? Oh, I put it in the dolphins, excuse me. Oh, sorry, I'm not finding this. I should put my sections labeled more clearly. Okay, here are the conditions right at the beginning. I'll just copy paste those so I have them as reference. Independence, we'll assume that's satisfied. Sufficiently large sample is N. This means greater than or equal to 30. Yes, we have a sample size of 100. I think that's what I saw above here. Yes, so in this case, we're good. We can just assume it's normal. All right, so then let's calculate the standard error. I guess notice I have the formula memorized. The only thing then you need to do is find out what S and N are. So remember, we're sampling from the 2017 race. So that was our mean, 97 minutes, standard deviation, 16.98. Okay, so that's our standard error. So I'll see if I can edit this video. Okay, so these are the correct values for the mean, the standard deviation, and the sample size. So we got the standard error. That looks better. Okay, so then we look at what is this distribution? What's going on here for finding our p-value is we look at our standardized mean time, which is this t-score. That thing is going to be distributed as a t-distribution with 99 degrees of freedom. That's just kind of a theory thing. And so we got the observed mean was x bar. We saved it up here, minus the expected mean. What was our null hypothesis mean? The previous race time. And then we divide it by standard error. Or you could do it this way if you like being the same as before. So that's our t-score. All right. And so this is helping us keep track of what we're comparing. And now let's find that p-value. Notice this value is greater than the mean. So we're going to do an upper tail, 1 minus pt of the t-score with degrees of freedom 99, 100 minus 1. So that's the probability of being greater than, this is the probability, I'll say this here. Being great of a mean okay, that's the p-value for the mean race time being greater than 93.29. But if you remember, our null hypothesis was not just greater, it was greater or less than, just not equal to. Okay, so when that's the case, we're looking at what's the probability of being this far away from the mean. And you remember we did that by doubling our probability, adding probability of being greater than that far or less than what would be negative that far. So that's the two-sided probability. You can use each of these for evaluating our hypothesis, as long as you use the proper hypothesis. But this is the p-value we'll use for saying the race times are different. We don't care if they're bigger or less, but they are definitely different. So we would say, since p is less than 0.05, we reject the null, which says that they're the same. So we have strong evidence that the race times are changing. Very nice. So that's a good example. You know, oftentimes we have to filter out our problem. What is the data we're comparing against what? What is our sample, and we're assuming this is the population. You know, we're assuming this is the baseline of some bigger phenomenon that we're only sampling a small portion from. All right. So in the last example, we have what's called paired data. And next week, we'll look at how to test if we're sampling from two different groups and want to see if their means are different. That's a similar test with some modifications. But when you have two sets of data in which each data point is corresponding, that's called paired data. And it's very nice because you can use the same test as before for paired data. So let's look at an example of paired data. You got book prices. Each textbook you buy, you could either buy at the bookstore or you could buy on Amazon. And those are two data points. but they correspond to one book, right? My stats textbook, price for Amazon, price for bookstore. We can look at those differences for each textbook and consider that as a t-test. So for this paired data, let's look at the prices here. Well, there's a lot of things going on here. You see there's an Amazon price and the UCLA bookstore price. We're going to look at, do these means differ, right? And the way to do that test when it's paired data is just look at the difference of the means. So if I want to find the difference of my variable here is textbook, I'm going to look at the difference of my UCLA new prices and the Amazon new prices. So if I look at that difference, here is a histogram of the price difference. See that 0 would be no price difference. On this side, these are books where the UCLA price is more. These are books for the Amazon price is more. So we're going to say, do the prices differ? Is there generally a better place to shop for textbooks? So we're going to find the mean difference. The difference, I'll show you, is the data we're looking at. We're conducting our test for the difference of our data. And so the mean difference is $12. You're paying $12 more for UCLA on average. Okay, and there's the standard deviation. So let's perform a t-test to show whether the prices differ. So it'll be helpful to put our null hypothesis, which says that prices don't differ. Mean price is 0, right? Price difference. And the alternate is going to be that the mean prices do differ. Okay. Mean price difference is not 0. So let's do a t-test for this. Okay. So what we need is our data, the difference for our data, which was the difference in the prices. The average difference, I should say. And S was the average, the standard deviation of the differences. And what was our sample size? How many textbooks? 73. 73. So with that, we can find our standard error. And by now, like I want you to be trying to do this on your own, right? And the t-score is the observed mean minus the null, the expected mean. What's the expected mean? If the prices don't differ, that mean is 0. There's our t-score. And let's see what our t-score is. 7. Okay, so what's the probability of observing something greater than that? And we had 73, well, let's say n-1, so we put it above. So that'll be our one-sided hypothesis. But all we want to care about is whether the prices are different. So if that's the case, is not 0, we got to double that. So we got to double that value. Sorry, I'll leave this here. That's the one-sided hypothesis, and the two-sided hypothesis will be below it. So you can see the difference. They're both really small, but we'll say that's our p-value, which is certainly less than any reasonable cutoff. So what does this tell us? Tell me. All right. Have a good weekend.